Right then, sorry for a bit of a delayed start, but getting the kit set up is no bad thing anyway, because we're ready to go a little bit easier once we start doing our practical for the week. Structure of the PLC. So part of the assignment's going to ask you to talk about the basic structure of PLC and how they operate. So I'm going to go through that this morning, and you can make notes as we go along. But in essence, the internal workings of PLC can be broken down into 4 general parts. An input interface, an output interface, a processor or processing unit, and a block that is the memory. So the figure on there shows the relationship between them. So the input interface feeds information into the processing unit. The processor unit sends information to the output interface so that can operate, and also the processing unit sends information backwards and forwards between itself and memory. So that's a sort of high-level block diagram of a PLC, and you don't really need to know in any more detail lower than that how it works. So, looking at each of those in turn, the central processing unit, starting with that, it's kind of the brain of the PLC. It carries out the program instructions, takes information from various places, processes it, and sends it off somewhere else. So it does no different to what the microprocessor does in your computer at home, your laptop, your phone, your iPad, or any other computing device. Really, it just does all the work. Yeah, and it does it quickly. So it receives, processes a control program from memory unit, and acts upon that control program using the information from the input and the output sections. The memory unit, 3 main functions. Stores the system of control. It stores your program, the instructions of your program. It holds images of the input and output statuses of every device connected to the PLC. What that means is it's got an internal memory of the last recorded state of all the inputs and all the outputs. So it stores that information. And a bit more about that in a little while when we talk about how the process works in a PLC, which is different to what the program is executed in a personal computer. Okay. It holds any data associated with the PLC's operation. For example, it holds the most recent input and output states, the current value of any timers, the contents of any counters, and any other data needed to run the program. So you may have your counter values and timer values held in data registers because you want to do other extra maths with those. For instance, if you count all your rejected bottles and you count all your good bottles, you can use maths to add those two together to get a total throughput for the machine, for instance. Not that I know of. But you could write 2 sections that you can switch between very easily. But you wouldn't call them a different program. You might use some kind of switch to make it jump one part of the program and only run the other part. So that you could certainly have options in your program, but as for 2 actual programs, not that I know of. Okay. I could be wrong, there might be one out there that does, but I don't know of it. So, moving on from the memory, input interface. This takes signals from sensors, push buttons, etc. So it's half of the PLC's interaction with the real world outside its box, if you like. Okay? So there's a world outside, the PLC needs information about that world. That information comes in from the input interface. So input signals are usually 24 volts DC. In some more expensive systems, you might find other values such as 5 volt, 110 volt DC or AC. Okay, but in general, if you go out and buy a fairly bog standard PLC, the input voltage is most likely to be 24 volts DC. To protect the internal workings of a PLC, the inputs incorporate opto isolators. What that is your switch, your sensor, if we look at this here, is connected to the input terminals of that PLC, and when you want to turn it on, you provide that with 24 volts. Okay. What that does is go through a little circuit with an LED in it, and then on the PLC side, the processor side, there's a photo transistor that recognizes that LED is turned on, and it turns the circuit on inside here and turns the actual input on as far as the PLC process is concerned. But what you've got is you've got electrical isolation between the outside world and the processor. So if we get a large spike on this signal here for one reason or another, a really high voltage or something goes wrong with that, we aren't going to affect we're not going to do a massive blow up on the internal workings of the PLC. We've got electrical isolation through an opto isolator. Okay, so that's quite common where you've got transistorized inputs. And I don't know of any PLC that doesn't use transistors with opto isolators on the inputs. So that protects the internal workings. There's usually a set of LEDs fitted, and you've seen them, there are little tiny numbers on the top plate of the PLC that light up when that particular input is turned on. So there's visual indication that an input is energized on the actual box of the PLC. Sensor wiring. So looking at the inputs, that's typical input wiring. Now, there's a 24 volt power supply, either built into the PLC that you buy, or you can, if you want to, put your own on if you need more current capacity, because things like sensors actually take a current from that power supply. A simple switch like this one will take a little bit of current to turn this input stage on, but not very much. But if you run lots of sensors, you might have a high current need for your inputs. You might have to put an external power supply in. There's a 24 volt power supply, and in this case, feeding through that switch to that terminal to turn on input X1, that particular switch there. So that's like a mechanical switch type input where we're taking, and it could be on some systems that it switches the minus side of the DC as well, and more about that in a little while. Okay. The other sensor that's on there takes a power supply, positive and negative, from the PLC's power supply or your external power supply, and then it uses a transistor inside. So when this sensors, if it's a sensor that senses metal, okay, then when a piece of metal comes in front of that sensor, what it does is magnetically usually sense that that's present and turn this transistor on so that we get a current flow through the transistor to the input and turn it on. So that could be a sensor that is a photo sensor, a reflective eye, or one with a reflector on it, or two sensors, or it could be Hall effect could be capacitive. There are thousands of different types of sensor out there. But because they've got an electronic circuit inside them, they need a power supply to operate. So they're kind of a 3-wire sensor then. Alright? And this particular one hangs off the positive and provides the positive to the PLC. Okay? And a bit more about that in a minute. Okay? Alright with that so far? So, source and inputs. 2 different ways inputs can be wired. The one that you've just seen is sourcing. It hangs off the positive. The transistor hangs off the positive. It's got a PNP transistor inside, and it provides the positive to the input terminal, with the negative being common. What it does is it provides the source. That's why it's called sourcing. Okay? Current flows out of the transistor when the sensor switches on. So our current flow is from the positive through the transistor inside the sensor, in that direction there, into the PLC. That's sourcing. And I'm going to get you access to my former colleague, Mr. John Draper, wrote quite an extensive and good, for this level, book about PLCs, and there's more information, a lot of information in there that could be helpful to you. So I'll make sure you've got access to that before your assignments are due. Okay? There's more in chapter 3 of John's book. Syncing. Okay? The other way to wire sensors is where the transistor in the sensor sits on the negative side of the DC, V minus, or 0 volts. Okay? It's also got a positive to it. But what happens with that is the current flows out of the PLC down through the transistor to negative. It sinks the current from the input terminal down to negative when it turns on. This is why choosing sensors is a bit of a minefield, because you've got to choose. You usually got 4 options to choose from. You've got to choose syncing or sourcing, and then you've got to choose normally open or normally closed, i.e. is it on when something's in front of it, or is it off when something's in front of it? So generally at least 4 options to look at when you pick a sensor. Some of them can be wired in any of them just by the way you wire them. Okay, but that you'll have, if you get a 4-wire sensor, then you usually got an option within it in how you wire it. Okay, so it provides the negative to the PLC terminal, and it uses an NPN type transistor inside. The important point for PLC selection and design, and I don't know about every manufacturer, but Mitsubishi, by the way you wire your sensor in, you can have either syncing or sourcing, but you cannot have a mixture of both. Yeah. So if you was ever in a position where you're going to retrofit a PLC to a machine that's already there and that's got sensors on it, you need to know whether that's syncing or sourcing, and they need to all be the same. It's not an issue with a simple switch, because that will work with either way round of wiring quite adequately. But when it's the 3 or 4 wire sensors, you need to either select all MPN or all PNP type, all syncing or all sourcing. Okay? Complicated, I know. I won't get too worried about it, because, you know, in most cases someone else has got to design the system, you're going to build it and just program it. You may never ever touch a PLC again. Okay? As far as your assignment's concerned, that's as much easy as much as you need to know. The output interface. The output interface, all output signals to the various actuators used on the equipment being controlled are connected to this. So what it is that's the other half of the connection with the outside world. We're taking this information in about the outside world, but we also want the PLC to control the outside world. We want it to turn lights on, turn motors on, open valves, close valves, and that type of thing. So the output interface does that. There are generally two types. You may find some manufacturers that have a third type of output. Relay. Okay. The advantage with relay is that they can take any voltage up to quite a high, usually 230 volts. Okay. They provide inherent isolation because they're just a set of contacts. So it provides the isolation that you saw with the octo inputs without doing anything else. Okay, and can quite easily handle either AC or DC currents. The disadvantage with relays is that they have a finite mechanical life and they aren't as fast in operating. More about that in a minute. Transistor type outputs, again they work on the principle of octo isolation but in the other direction. So the signal from the PLC turns a little LED on which switches the output transistor on and provides current to the valve, light or whatever it is you want to turn on. They are much faster in operation, if fast operation is important. Okay, they have a higher life expectancy because there's nothing mechanically moving about them that there is in the relay, so they've got a mechanical life. But they are DC only, and they will only accept a narrow band of voltages. So if you're looking at switching high currents and higher voltages, you're going to have to put some other interface in between the output and that high current device anyway. And you would probably also have to do that for a relay. So if you've got a big 100 horsepower motor you want to start and stop with your PLC, you ain't going to do that directly with the outputs. You're going to have some high current contactors in between the PLC and that motor. And that table kind of summarizes the difference between the two types. Relay, operating voltage 5 to 250 volt AC or 5 to 30 volt DC. 2 amp resistive load, 80 VA inductive load. Approximately 10 millisecond response time. So 10 milliseconds, 1/10 of a second to operate. Pretty quick. But then look at the transistor, less than 0.2 milliseconds to operate. So quite significantly faster. But can only handle DC voltages between, for Mitsubishi anyway, 20.4 volts and 28.8 volts. And the load much lower, only half an amp resistive, 12 watt inductive load. Okay, so there's a trade-off between the two. And one thing, if you go in either the mid-range, i.e. that we talked about last week, or the rack-mounted, you could buy in the mid-range, you could buy a base unit with relays and buy an extension unit with transistor outputs. So you can mix them a bit. You could buy a relay output card for your rack-mounted type, and you could buy a transistor one. So you could mix and match what you do with your outputs in the higher end PLC type, where you've got options and extensions that you can add. We're going to move on to now, there's a little bit more detail in how this PLC operates this program that we put into it. Just going to try and get this slide so you can actually see all of the diagrams. Okay, and I know you can't necessarily see the writing on the screen, but you've got your handouts. So when you switch on the PLC and put it into run mode, okay, what it does is it starts to go through this cycle around here. Okay, the first thing it does on starting is delete the output memory. Okay, what it then does is it looks at the input terminals, all of them, every single one, and records their status in memory, whether they're off or on. Yeah. So it takes a snapshot of the current state of all the inputs and stores that in a reserved space in memory. Then what it does, so it's gone through there, done that, comes to the first instruction in your program. Okay. So the first ladder line, let's say your first ladder line is like this, X1, Y1, something like that. Okay? And then maybe your second ladder line, something like this. For argument's sake. So it hits this first instruction, and it says, what's the current state of X1? It doesn't look at the actual state, it looks at that state as stored in memory. Yeah? And if that's on, it then says, right, I've got to turn Y1 on. It turns Y1 on in memory at that stage, not the real output Y1. Okay? So if this is on, if that's blue, like you saw on the screen last week, it'll turn that blue, but the relay hasn't turned on yet. The lamp connected to it hasn't turned on yet. It then moves on to the next line of the program, and if that one's blue, it'll say, I need to turn that one on. It'll turn that on in memory. So it'll put a 1 in whatever section of memory is designating the status of that output. It then goes through all your programs step by step, okay, until it gets to the end instruction. What it does then is it goes down through here, transfers the current status of all the outputs to the output section of the PLC. That's when these two relays turn on. Okay, and then it goes back up the top and does that again. Typically, I'd say it all depends on the length of the program. Every instruction takes a certain amount of time. Not all of them take the same amount of time to execute. So if you've got a long program, it's going to take longer. What is important is for the same loop, it's consistent, so it always happens in the main amount of time. I'm kind of guessing, but let's say 50, 100 milliseconds at most to do a scan, probably less than that. Yeah, I'd have to look it up, and when you do your assignment, you might do that. Okay. The implications of that. So the main advantage of this scan, let's just move on to the next slide, is that for a given program, the scan time is fixed and constant. Yeah. So it will act in a consistent way. That's very important for industrial systems. We want them to take the same amount of time to do things all the time and not inconsistent. The disadvantage is if income and digital signals are extremely short, they can be missed. Going back to this example, I'm just going to clone that page, I think, and make a copy of it. If we go back to that, let's take that and that off. Look at it. Right, going back to the top end, if on a particular scan, right, so if on a particular scan we hit this bit here, all inputs, and X1 at that point is off. Yeah, I'm going to deal with just X1. At that point that's off. And this step is number 100 down the line there somewhere. It's not the first one. Yeah. So it's done all these other instructions. In the time between going from step 0 to step 100, after that's recorded that that switch is off, X1 actually turns on in real life. So here's the real life X1 over here, and it turns on. It goes to 1, on. This part of the program is using that version, so it won't turn the output on. Yep. Now if that input there turns off again before it comes round to the top and pulls the inputs again, that signal will be completely missed. So very short signal pulses can be missed. There's also, if that switch turning on is just after it's done that poll, right, it's got to go down through the program, even if that's a permanently on long signal, it's got to go down through all the program, back up to the top, pull them inputs again, and go all through the program again, virtually 2 full scans before the output turns on. So there could be that much inherent delay in a signal being made and the output reacting to it. It's consistent, but there's a possibility of those delays, and if speed and time is really important, that could be an issue in some cases. I don't think, certainly at this stage, you're not going to be writing programs where that is an issue, but you should be aware of how this thing operates, and it doesn't operate in the same way as that thing there operates, or the processor on your phone. It's much more able to dart off and do other things using interrupts than the PLC program is. You can use modern PLCs have the ability to use interrupts. The danger with interrupts in systems of where control is important is it's difficult to test what's going to happen when that interrupt happens under every possible scenario that might happen. So that's something that you kind of tend to avoid unless you really have to do it. Right? It's a very advanced way of programming, and only done if there's an advanced need for it. I've never had to do it. Okay? So that is kind of as simple as I can make an explanation of how this mass copying. So mass copying is that you copy the state of these, you scan the program, and then you mass copy the result of that into the outputs, and you keep repeating that over and over and again, and refreshing it in a scan cycle. Okay, not a major issue for a large number of a large proportion of applications, but it's something that you should be aware of in your programs. Also, it's the reason why something else we're going to talk about in a little while, double coiling, is an issue. This man here remembers double. Thou shalt not double coil, right? Am I right, Jordan? Yeah. because that scan means that you could in one scan try to turn the same output on and off in the same scan, so it doesn't work at all. It either stays on or it stays off, and we'll be looking at that problem and demonstrating why you shouldn't what's called double coil. The software doesn't pick that up as an error, because in some programs where you have subroutines you could actually use an output twice, but you shouldn't do it in any one routine. Yeah, alright. So you mustn't mention the same output twice, and we'll be on to that shortly. Okay, so just to look in more detail around the system, relay control system. Just quickly go through what we've got here is a motor. It is the let's say that's the hydraulic pump. Okay, that's switched on and off from a three-phase supply using a contactor. Yep. So what happens is we've got a start button here, a stop button there, normally closed. You're not going to get used to that. Stop buttons are wired normally closed, so they're fail safe. If the wire falls off it, thing stops. Okay. That's the start-stop circuit there for that motor. We push this button here, that switch closes, we get current down there to that relay coil, which closes those three, and the motor starts up. This contact here, there's a latch, you're going to get used to those as well, providing a second current path, so that when I take my finger off the button, the motor still runs. Start, stop, latch. Easy. You're going to need to program loads of them. Alright? When I push that stop button, it breaks that circuit down there and stops the motor. Alright? Then what we've got over here is something like a hydraulic stamp. So there's our hydraulic valve here, controlled by a relay. Here's the relay one that turns that one on. We've got a push button here. When we close that, it goes through the limit switch, which is normally closed, turns that relay on, closes that, and the stamp comes down. The limit switch is on the end position of the stamp. When it hits the end position, it breaks that circuit, turns the valve off, and hydraulic ram goes back up again. So that's just like a little, I think I designed this as like a paint can, put the lid on a paint can type of hydraulic stamp. So it comes down, when it hits the limit switch, knows the paint lid is all the way on, and then goes back up again. So that's how you would hardwire that in a relay panel. If we try and convert that system to PLC control, that's how we would do it. Here's our motor start stop button there, into one input, X0. There's our stop button into X1, our stamp button into X2, and the limit switch into X3. The way those interact with each other is the job of your program that you write. And then coming out at the bottom, there's your two outputs. Contactor C1 for the motor, and the valve, stamp valve. Okay, but this bit is exactly the same as it was before, controlled by that contactor. Okay, the difference between those two is, let's say we found the lids weren't quite going on properly, and we wanted the hydraulic cylinder to stay down a bit longer and force it on. All we've got to do is change our program so it's got a timer in it, and when it hit the limit switch we start a timer, and then when the timer time out we bring the hydraulic ram up. Okay? All we got to do that on this system is change the program. On the old system, that one, we would have to open the panel up, mount a timer, wire it in, change all the wiring so it worked how he wanted it to do. So it's a very simplistic example, because don't think every alteration to PLC system can be done without external wiring, because that may well not be the case. But it does simplify modifications in some cases. You're all kind of happy with that, yeah? Right. I'm going to pause the... So, makeup of a ladder rung. All ladder rungs consist of at least one logic instruction, one contact, yeah. Switch might be from an output, might be from an input, might be some kind of internal function, okay? But there'll be at least one thing that end, a logic instruction or instructions. Tell them some kind of coil or other instruction to turn on, off, store a value, or do some other function. So there has to be something connected to the left-hand rail and an output or other function here connected to the right-hand rail. This bit here can be very complex or very simple depending on the function you're trying to get it to do. So that's the bare minimum. It's one thing at least that end, and want some kind of output the other end. So, the structure of a PLC logic instruction. Program instruction is represented in a ladder diagram as the instruction type. This particular one is a normally open contact. That's the instruction there. Sorry, did I give the wrong page number? Ah, yeah, because you've got a Word document set of notes extracted from this. My apologies. Yeah. And then above that is which device that contact is attached to. So the X is the device name. X is equal to input from the outside world. Okay, and then this one is the device address or the particular number of that input. And on your PLCs you've got, I think that's X0 to X7. Yeah, you've got 8 inputs. Okay. It then goes, if you had more, it then goes to 10, because it's a legacy thing, but the inputs work on octal. An octal number, base number and system for some reason. Okay, so that is the inputs. Just have a quick look what I've got on the next slide. Okay, yeah. Now, contacts are device types for logic instructions. So any contact can be associated with, so the letter is used to tell you the type of device it is. So, logic instructions can come from inputs, switches, push button sensors, i.e. the outside world. It can be using the logic that another output is turned on, so you can only have the coil of an output once, so you don't double coil, but you can have as many contacts to tell other things to turn on when that output come on as you like. Okay, so that can be, you could have a Y on a contact. You can also have them associated with timers, with counters, and with M relays. M relays are internal relays used to create more complex logic, and most importantly help you to avoid double coiling. More about that later. So T2, if the device was designated T2, it would be timer number 2, and Y4 would designate output number 4, etc. Okay? And there are, on your PLCs, there are 6 outputs and several hundred internal relays, 100 or more timers and counters. And then with the timers and counters, some are 0.01 pulse, some are shorter pulses, so you've got a range of different resolutions that you can work with your timers as well. Okay, but more about that when we look at timers and counters. Then, and I know some of you who got a little bit further last week had a go at some of this anyway, but I'm kind of just trying to formalise it. 2 basic types of logic instruction. Normally open. The term normally is used to designate what state is that contact in when its element X0 is off, in this case. So if the input X0 is off, that contact will be open. If the input X0 is on, that'll be closed. So normally means what state is it when that input or that device is off. The second type, where the diagonal line across, is normally closed. So when input X2 is off, that contact will be closed and effectively turned on. If we turn the input on, that contact will open. So it works the opposite way round, commonly known as the inverse instruction. Note, when monitoring a program, so you had a little bit of a go at turning the system into monitor mode last week with a laptop, and you saw that elements go blue. If an element is blue square in it, the contact is closed regardless of type. Yep. So you always know when they're closed because they have a little blue square in there. And it makes sense that those two, if you have those two in your program, they can never both be on at the same time, because they're opposites of each other. Okay, everybody happy with that so far? Building logic functions. So some of you might have already had a go. If you have, that don't make any difference. If you haven't, then you're going to have a go at building some basic logic functions this week. Okay. 2 basic types of logic instruction used. These are AND, or series logic. Things connected one after the other in a line, in series. You have to turn them all on to get the end thing to happen. And then we got OR parallel logic. We will look at the 2 separately. These types can be used in combination to create more complex logic functions. So AND logic. This ladder rung carry out the following. If input X2 and input X3 are turned on, the only way we can get that to turn on is turn them both on, and then that will do that. Another way to look at this is via a truth table, where we put all the possible combinations of input, so they're both off, switch 2 is off and 3 is on, switch 2 is on and 3 is off, or they're both on, and then we designate what the state of the output is for each case. And you could do that for any number of switches. Okay, so when you come to this bit, I ask you to have a go at writing that program and testing it to see whether you get it to work, and modify the program so light 2 only comes on if switches 2, 3 and 4 are turned on. So that involves you adding the extra input contact in series with the other 2. Okay. one point is, when you're testing, and that's not a serious issue with these very simple programs here, but what this bit means is, in all examples, make sure you test all switch combinations. That means you should go through the truth table, making sure you get these results for those 4 input states. What you're doing is, you're not just checking that your program does what you want it to do, turn that light on when both switches are on, but also that it doesn't do what you don't want it to do, turn the light on when only one switch is turned on. And that's a simplistic example here, but programs should be checked to make sure that there's inbuilt, I don't want it to do this, check to make sure it doesn't do that. Okay? And that's about designing good testing routines, which will be part of your main programming assignment. The AND instruction we've normally closed, so this logic is going to turn the light on only if both of them are off. So the truth table has had the on moved up from the bottom one to the top one. Okay, have a go. Make sure you understand how these simple logic configurations work, a simple AND, OR, and their inverses. It will help you a lot if you can really understand what they do and what they'll give you when you write more complex programs. Then the other option is the OR logic. OR logic with 2 inputs. This is where we get a parallel circuit. We get an alternative, one or more alternative paths. This case, the light will turn on if we turn that one on. We've got a path to there. Or we turn that one on, or we turn both of them on. So our truth table has only got one condition with off in it for the output. The rest of them are all on. Yep. And again, there's some options for you to try, add on a little bit of additional functionality to that program. Or logic with normally closed instructions. So that makes the only off is when both switches are turned on. Okay, so what you could do is you could write a truth table for what you want to happen with your outputs and then design some logic to achieve that. Yeah? Not necessarily the easiest way to go about it in this case, but you could do. Depends on what your application is as to whether a truth table is that relevant or not. Combining OR and AND logic. So this is kind of where I'm starting to get you to start thinking about writing a program for yourself. Sketch out try and get into the habit of sketching out something you think will work. Put that in the PLC, test it against what you're trying to achieve. If it doesn't work, looking at what is happening and why it isn't doing what you thought it would do in the first place and making alterations. One thing that happens with inexperienced programmers that don't get this too well to start with is they always think if they've got a problem with a program, they've got to add something extra to get it to work. That's at least half the examples is that you ain't got to add something, you've just got to change something. Yep. And that might be going back and changing something that you already started and got working, one section of your program that you had working, but now you're working on some additional functionality, it doesn't work anymore, and you've got to go back and make some alterations to it. So try and avoid that every problem needs me to add something new, because that may not be the case. Could be, but not always. And my recommendation is when you get a specification for a more complex program, you build your program in blocks and you test each bit as you go along before you move on to the next bit of functionality. That way you know you've got something to work, and the only bit that could cause a problem is the bit you've just changed. The small one single rung that you've added or the change that you've made has caused a problem. So you focus on why that caused a problem rather than changing all the bits that were working in the first place. If you go and try and write loads of logic all in one go and expect it to work, it probably isn't going to. Yeah. Also, this thing about sketching something on paper, there's an old saying in computer programming, the sooner you start to write the code, the longer it'll take. If you do the groundwork and have something that you think is going to work and you know why you think it's going to work, that's more likely to when you actually do write the program and write the code. Okay, so in here we've combined, in this one, I've combined AND logic there with another bit of AND logic and an inverse, and I've ordered the two together. So this light is going to turn on if X2 and X3 is on, or X4 is on and X5 is off. Yeah. So it's got two paths, but in both of those paths there are two switches. And you may end up coming up with a little bit of logic that's a little bit more complex than that in your programs. Just depends the way you go about it. And then the last bit is a challenge that I'm going to leave you to try if you haven't already. And that is write a program, turn on light 2 when switch 2 is on and switch 3 is off, or switch 3 is on and switch 4 is off, I think I should say. Yeah. When switch 2 is on and switch 3 is off, or when switch 3 is on and switch no, hang on, no, that's it. I thought I was on the extra challenge. That one's right. These extra challenges down here. Write a program to turn on light 5 when switch 6 or switch 7 is on, but not both. And then, can you think of an operation with two switches like that in the home? Okay, so those that haven't had a go at those basic logic stuff this week can have a go at working through those, trying out each one as you go along, making sure that you understand what they do. Yeah. If you've already done all of that, and I think there might be one or two that have, then if you give me a shout, we'll sort out something else for you to have a go at. Alright? So, this edition PLCs have a large number of internal relays or end relays, because they get the end in front of the number. The FX3Gs have the following internal relays available. There is a general type N0 to N403, so you've got 384 internal relays there. It's flat, you've got a pitch type. There's some kind of type that will hold their status even when you turn up the power. There's a problem with 52 there. There's more general. Connected to Y0 with X0 being a normally open momentary start stop button, Y1 a normally closed momentary stop button. Devise a program to carry out the following function. So it's going to take me through an exercise to design a program to do that function up the top there. So we've got a motor connected to Y0, X0 being the normally open button. So you're going to be using the green and red buttons on your input simulator to do this, okay? And then Y1, instead of a motor, you've got a light. So we're going to kind of simulate this action. To turn this Y1 stop button will stop it. So you're going to have that light go on a stop-start circuit. X2 is a switch between run and inch in operation. So what that means is, in run, you push the button, let go, and it keeps running. But in inching, you push the button, and when you let go, it stops. Okay. There's some help with this, if you need it. Devise a program that will carry out the following. When input X2 is on, push XO, motor starts, latches, so it stays on when you let go of the button, and when you push the red stop button, it stops. When X2 is turned off, push the start button should allow the motor Y0 to start, but when the button is released, it stops again, inching. So you can inch the machine along by pushing the button and letting go. Okay. Now you're given what might be an initial design idea for that program on this page. Start button, inch switch. So if both of those are turned on and the stop button hasn't got someone's finger on it, that'll be closed. Motor will turn on. This will close. We've got an alternative path, and that'll run. Okay. If we turn the X2 switch the other way, we stop the motor. Sorry. Turn the X switch to the other way so that it's on inch. Then if we push the start button and hold it, the motor will run, but as soon as we let go of the start button, it'll stop. So you're given that program and asked to try it out. And what you do, you'll find it doesn't work properly because you've double coiled. Yep. Enter that program as it is, test it, and see what happens. Then you're offered a potential solution with M relays. What's been done here, and you notice I've started to document these programs now. You've got a section up here, automatic section, run motor latched on M0. So same bit of circuit there, except this instruction's been changed from Y0 to M0, and we're turning on an internal relay called latch motor. So that bit is the same as that, except that instruction and that one's been changed to an M relay. Then the second one is the manual or inch section. That's exactly the same as the original, except this has been changed to a different M relay, M1. Then what we've done is written an output section where we've got or M1 will turn on the motor we want to run. And we haven't double coiled that output anymore. Okay? It's also a first start into showing you how a program could be structured. And if you can do this, have an output section, and I always tended to have mine at the end, where all my Y's are all in one place. Because if you're going to fault find, that's probably because some output or another isn't working. That section of the program will be where you want to look. And instead of having to hunt through the whole program of several hundred instructions, you'll know if that's well structured, you go to the output section, look at that line of the program, see what isn't happening there, and then go to other areas of the program to find out why that isn't happening. Usually it's going to be something to do with the outside world. An input's not on, made or something, a limit switch is not working, the sensor's not given an input. Very rare is it an error in the program if that's been well tested in the first place. So really make sure you go through and do that exercise, and definitely do that and save it as double coil problem solved, because I'm going to use that program in the how to do your documentation section. So you enter these rung comments and how you put in all the names of these things so they've got some kind of meaning. So we're going to use that program to actually do that. So make sure you've got that one saved somewhere. Special function relays, M8000 onwards. More advanced functions generally beyond the scope of this course. However, there are a few useful ones outlined in this diagram, which is not that visible on the screen. Okay, but M8000 is a run monitor, normally open contact. So that one, M8000, turns on and stays on when you switch to run mode. Yeah. M8001 is the same thing, but normally closed, so it turns off when you switch to run mode. Then you've got two that give you a very short pulse, just at that instant you switch to run mode. Whenever we talk about a short pulse in terms of these instructions, we're talking about a pulse so it turns on for one of those program scans. So just a very quick flick on, flick off. Very useful for things like resetting all your timers, resetting all your counters, resetting all your data registers if you've got them in a program, initializing certain values. You only need to do it very quickly in one scan, done and finished, and then the machine can start up. Okay. We've got M8011 as a 10 millisecond clock. What that does is turn on and off again once every 10 milliseconds. So it's like a pulse. You've got a 10 millisecond clock, a 100 millisecond clock, a 1 second clock, and a 1 minute clock pulse. So they are some useful additional special function relays that you might find useful in your programs. And there are 200 or 300 of them, I think. Something like that, might even be more. Timers, designated by the letter T to identify them, and then your X3G type, T0 to T199, 200 points, they are 100 millisecond timers, so they go in steps of 0.1 with regards to their time. 200 to 245, 10 milliseconds, so you can set them to values in 0.01 of a second resolution. There is a retentive type. That means they hold their current state using the battery backup when you turn the power off. 0.001, so they'll go to a thousandth of a second resolution, but only go up to 32.767 seconds. So there's a limit on how much you can put on them. The essence there is if you want a time to accuracy of a thousandth of a second, are you going to want to do really high values? Probably not. Okay. And then there's some test timers, i.e. battery backed, with 0.1 second resolution. Okay. So if you use the basic ones from TO upwards, that's all you're going to need for the programs you're going to write. Okay. 0.1 of a second resolution. Now, the way you program a timer is that you put the output coil instruction in. So you do output coil as the thing you select in the PLC, and then you put the T number, T1, then a space, and then K30. And that would mean a 3-second timer. You've got to multiply what you want in seconds by 10. Because that's doing a 0.1 of a second pulse when it counts down. So you want a 30-second timer, put a constant of 300 in. and there is a space in between this, the timer designation, and the constant. Okay. It's also possible, if the need arises, to have that not as a constant, but the contents of a data register. If you wanted your PLC and your program to be connected to an HMI and have people able to alter this timer value from 3 seconds to 3.5, then you wouldn't use a constant. You'd use the contents of a data register that was accessed backwards and forwards by that HMI, so it could be changed. You're not going to do any program that requires you to do that, but it's worthwhile knowing that that is possible. Okay. So what happens with this program is, when we turn this on, X0, T1 coil comes on, it starts to count up to 30 in 0.1 of a second pulses. When it gets to 30, it's said to have timed out. Yeah. This contact closes, and the output turns on. So it's like an on-delay timer, that circuit is. If we look at this, it tells you what happens. If we let go of X0 before it gets to 3 seconds, it resets back to the start again. Okay, and you should be aware of that. Haven't reached 3 seconds, so it turns off, and nothing happens with the output. It's only when it times out that the output turns on, and then that output will stay on until we let go of X0 and the timer resets. So there's the timer being off, there's the timer going through its timing period. When it hits the constant value, it's timed out, and then when we take the supply off it, it resets. Okay. When a timer times out, normally closed contacts associated with that timer close. Normally open contacts associated with it close. Normally closed ones open, and then when it resets, they go back the other way. Open ones go open, closed ones go closed. And you can have any number of contacts associated with a single timer that you want in your program. Okay, whereas with hardwired, you might be limited to 2 or 3 sets of contacts on your timer. But here, as long as we fit within the amount of memory we've got in our PLC, we can have as many contacts as we want associated with that timer. Then you'll be offered the opportunity to go through some exercises playing around with timers. I'm going to go through them in detail on here. By that stage, I'd like you to be in a mode where you're going to kind of have a go at it, because without doubt, learn much more by writing a little bit of program you think will work, and if it doesn't, learn why it doesn't work. If I wrote all the programs and you input this, test it, does it do what it wants to do? Yes. You'd learn very little from this experience. It's about getting things wrong and working to put them right in this class. So when you ask me for help, that's going to be, well, why? I'm going to be coming and saying things like, well, why do you think this isn't working? Let's have a look at it. What is happening? Why do you think that's happening? Rather than you need to change that to an X3 or this to an M5 or whatever. And I probably wouldn't even know what to do anyway. Okay. So there's some basic timer programming tasks for you to do in these notes. But make sure you've done all the first basic logic ones first, please. There's one that will be, this one is particularly useful, could be particularly useful later on, because there's a cycling timer where it'll turn a light on for X number of seconds and off for X number of seconds, and keep repeating that for as long as you've got it switched on. So when you have a go at your pedestrian crossing, you want to flash your amber light, you might want to come back to this little routine and incorporate that into your new program. And then just go through